So this is a follow-up to how to solve non-homogeneous differential equations in this form. And if you haven't watched that video, I would advise that you watch that video because I'm gonna skip over a few things so that way I kind of just get to the main point of this video. So if you recall, when we solve these types of equations, we're gonna assume a solution y of x or y1 of x is equal to e to the rx, where we have our y here. We pretty much plug this into the equation and solve for r. We would have to do the quadratic formula and we would get two different numbers of r, and we would have two solutions, and we could get the general solution for these differential equations. So we would have y1x, and then we would also have y2 of x, which we would have a different value of r. So in this one, I'm gonna put capital R of x. And yeah, so let's say for the main point of this video is, what if when we're trying to solve for r, we get a complex number. So a complex number being r is equal to alpha, which is a real number, plus I beta. I is the complex number, the square root of -1, and beta is just another real number. So when we solve for r in these cases, we would technically get two values of r. So we would get r1, or I'm just gonna keep it as, so this is gonna be our first value of r, then our second value of r is gonna be alpha minus IB. So here, yeah. So let's say we were to get these type of numbers when we try to go solve for r. What would be our solution in this case? So what we could do is just plug this into these two different solutions. So we get y1 of x is equal to e, then we just put this complex number. So alpha plus I beta of x. Same thing for here. I'm gonna put the capital R case. So we have e to the alpha minus I beta of x. Here, what we could do is kind of expand it. We could use the exponent identities, or whatever you call them. So y1 of x is equal to e to the alpha x times e to the I beta of x. We pretty much separated them. So now this one is in terms of a real number, e to the alpha of x, and this one's a complex number. Same thing for here. We could do the same thing. So here we have e to the alpha of x times e to the negative I beta of x. Okay, so now we have these two. What we're gonna be doing here is, if you're not familiar with it, we're gonna use Euler's formula. So Euler's formula is e to the I theta is equal to cosine of theta plus I sine of theta. So this is what we're gonna be using to kind of turn this into like to kind of get more real numbers, I suppose, from this. So y1 of x, e to the alpha of x, so this stays the same. And for here, our theta in this case for here is going to be beta times x. So instead of having the thetas here, we're going to put beta of x. So here we have cosine beta of x plus I sine of beta of x. Okay, same thing, we could do it for y of 2. So we would have e to the alpha of x times, and in this case, I'm gonna put the negative, just to make it more clear, I'm gonna move that negative and kind of just put it in front of the b, but I'm gonna put parentheses just to make it more clear. So now our theta in this case is gonna be negative b of x. So we have cosine negative b of x plus I sine negative b of x. Okay, so now that we're at this point, we could expand this part of y1 of x. So we have y1 x is equal to e to the alpha of x cosine of bx. So now notice how this part right here is just all real. This is just some real number. And as for this part, this is going to be a complex part. So I'm just going to put the I in the front. E to the alpha of x sine beta of x. So this is our solution for y of 1. And for this part, cosine negative b of x, because cosine is an even function, we could get rid of this negative part right here. And for sine of negative b of x, it's an odd function. So instead of having the negative on the inside, we're just going to put it on the outside. So now we have that right there. And the same thing, we could expand it. So y2 of x is equal to e to the alpha of x cosine beta of x. Again, this part is real right here. Then we would have minus I e to the alpha of x sine beta of x, and yeah. So notice how these two parts are similar. We have a real number in both cases, and we also have a complex number in both cases. And yeah, we're gonna go more further with this. Okay, so now that we solved for our solutions, y1 and y2, notice how they kind of look the same. Again, we have our real parts here, we have an imaginary number here, and we have another real part here. So what we're gonna do is have another function, that is the wrong marker, but we're gonna kind of do it for the general case, I suppose. So z of x, this is a new function, and that's gonna be equal to u of x, which is this part right here. It's a real function of x, plus I. Then for this other real part right next to the imaginary unit I, we're gonna have another real function of x, and we're gonna call that v. Now this one applies to this top one, but if you want to, you could go ahead and try solving for the minus case yourself like that. But as we do these steps, you're gonna come to realize that you're gonna get the same solution. So right now we're just gonna deal with the plus case. So let's say this function right here is a solution to this differential equation up here. Well, if it's a solution, we're just gonna plug it in. So we have a. If we take the second derivative of this part, I is just a constant. So when we take the second derivative, we're gonna get u double prime of x plus I, then v double prime of x. Same thing with this second part right here, b. We're just gonna do the first derivative this time. So u prime of x plus I v prime of x. Then c, and then this is just the same function. So we have u, I gotta make sure I write that right. So we have u of x. Also, sorry if I write my u's weird. I kind of just have a habit of writing it like that, but plus iv of x. And that's going to be equal to 0. Now let's just get the u's and v's together. So we have, for our u's, we have a times u double prime. So a u double prime of x. And then here is b u prime. So b u prime of x. Plus, then we have c times u. So c u of x. Same thing with the v's. However, for all these v's, we have an I. So we're just gonna take I on the outside and then just put all the v's together. So a times double prime v, a v double prime. Then v prime, then I'm sorry, this is getting like a bit of a tongue twister, but we have b v prime of x plus c v of x. Okay, get that complete tongue twister out of the way. Okay, now we have this. And just to make it more clear, I kind of don't like how that's written. So I'm just gonna make it so that we see the parentheses, just kind of, bam, okay. Now, remember, we said that z of x is a solution for this homogeneous, or this differential equation. And in order for this part to be 0, then in order for all of this to be 0 really, is that we have this part right here that has to be equal to 0. And then for this imaginary part, this real part right here has to also be equal to 0. So really at the end, we're just left with, I'm just gonna erase this so that way I get more room. So we're left with two different equations. So AU prime, I'm just gonna write the prime. So BU of prime plus C of U. This has to be 0. And then same thing for this part right here. So AV double prime plus BV of prime plus C of V has to be 0. Now notice how, again, Z is a solution to this differential equation. But as we can see here, we don't even need to care about this I, this complex part. Our U function and our V function are real solutions for the differential equation. So really, we don't even need to care about the I. And again, if you did this with minus at the start, so that, you just come to the same conclusion here. And because we don't even care about the imaginary parts, we really have two real solutions for this differential equation. So here are going to be our real value solutions for this differential equation. So we're not going to be using this for our solutions, y1 and y2. We're going to be using these for our solutions. And this is going to be our solution whenever r is a complex number. You just find out what alpha is and beta is, just plug it in, and you'll get the real solutions for kind of like this complex answer, if that makes sense. And yeah, we'll go over some like practice problems. Okay, so here we have a differential equation, and this one is gonna have complex solutions to it. Or really, when we solve for r, we're gonna get a complex number from it. So let's just do the same thing. Assume the solution in the form y of x is equal to e to the rx. When we plug this in, we're gonna get, or I'm just gonna skip to the auxiliary equation. So we're gonna get r squared minus 6r plus 10, and that's gonna be equal to 0. Solving for r, we're gonna use the quadratic formula. So r is equal to negative b, which that's just gonna be 6, right here, positive 6, plus or minus the square root of b squared. So that's just gonna be 36, minus 4, we have 1, and then for our c, we have 10, all over 2a, which is just, our a is just 1. Further solving for r, we get 6 plus or minus, so here we're gonna have 36 minus 40, we're gonna have the square root of negative 4 over 2. This negative 4 is just gonna be 6 plus or minus I2 all over 2. And then for r, ultimately we get 3 plus or minus I. Okay. So this is our two values for r really. And our alpha, what we're gonna do right now is, because it didn't matter which is plus or which one's minus, we're just gonna spot which ones are, what number is our alpha and what number was our beta. So I should probably write the solutions. So we had the solutions in the form of e to the alpha of x cosine beta of x, and we had y2, which is e to the alpha of x sine beta of x. Okay, from this complex number here for r, we could see that our alpha in this case is going to be 3. And then our beta in this case, there's secretly like a 1 here. This is going to be our beta. So now we just plug these into to our two solutions, and yeah, we pretty much solved the solutions for this differential equation. So when we plug that in, we get y1 of x is equal to e. So our alpha is 3, so we have 3 of x. Then cosine, our beta is just 1, so we have cosine of x. Then we have y2 of x is equal to e to the 3x sine of x. So this right here is going to be our solution for this differential equation. Simple as that, pretty much. And yeah, we'll go over another problem. Actually, before we close off this problem, for our general solution, I almost forgot about the general solution. But our general solution is going to be the same thing, where we have our c1 y1 plus c2 y2. We could just plug them in. So y of x, our general solution is going to be c1, then our y1 is just e to the 3x cosine of x, so e to the 3x cosine of x, plus c2 e to the 3x sine of x. And this right here, as you may know, will help us solve for initial value problems. And yeah, this right here is going to be our general solution. These are fine, they're right, but this is the more general solution for this differential equation. And yeah, next problem. So here's our next differential equation. However, we're going to use initial points to solve this differential equation, and yeah, let's just get right into it. So again, I'm just going to put the auxiliary equation right away. So we get r squared plus 2 of r plus 17 is equal to 0. So again, using the quadratic formula to solve for r, we get negative b, which our b in this case is 2, so negative 2, plus or minus the square root of, so we're going to have a 4 right here, minus 4, our a in this case is just 1, c is 17. I actually don't know 4 times 17 off my head, but then on the bottom we have 2a, so we have 2. So we're going to have a negative 2 plus or minus the square root of, so here we're going to have negative 64 all over 2. The square root of 64 is 8. I'm just going to put the I on the outside. So we get negative 2 plus or minus 8i, or I'm going to put I8. So I of 8 over 2. Then we get r is just equal to negative 1 plus or minus I4. So here's our r. Right away, our alpha in this case is going to be this negative 1 right here. So alpha is equal to negative 1. And our beta is equal to the 4. So I'm just going to write them down again. So our solutions was e to the alpha of x cosine beta of x. Then y of 2 is going to be e to the alpha of x sine beta of x. And so if we just need to plug in alpha and beta again. So our two solutions are going to be y1 of x is equal to e to the negative x, because alpha is just negative 1. So negative x cosine of this, 4, yeah, 4 of x. And then our y of 2, same thing, just plug in alpha alpha with alpha and beta with beta, we're gonna get e to the negative x sine of 4 of x. So really the only thing that changes between these two solutions are the cosine and the sine. And our general solution for this problem, y of x. And again, we need the general solution to solve for these initial conditions. So we're gonna get c1 e to the negative x cosine 4 of x plus c2 e to the negative x sine of 4 of x. So now we're going to be using this to solve for that. Okay, so here we have the general solution for this differential equation. And because we're going to need y prime, we're going to have to take the derivative of this y of x. But the first thing that I'm going to do is apply this. So all of our x's are 0, and this is going to be 1. So 1 is equal to c1 e to the negative 0, that's just going to be 1. Then cosine of 4 of x, or cosine of 0 is just going to be 1. So we're just left with c1 plus, and if this turns into 0 over here, then this whole thing is 0. So we get c1 is equal to just 1. So bam, we got that. Now we got to do the y prime of 0, so that way we can solve for c2. So our y prime of x, c1 is just a constant. Right here we got to do a product rule. So we get c1. I'm going to take the derivative of this part first, the e to the negative x. So I'm going to put the negative on the front there. E to the negative x cosine of 4 of x plus, then we're going to take the derivative of that, which the derivative of cosine 4 of x is going to be negative 4 sine of 4 of x. So we get c1 e to the negative x. And I'm just going to put the 4 right here. Squeeze it in. Then sine of 4 of x. Same thing over here. We got to do a product rule. So I'm going to take the derivative of e to the negative x first, which gives us a negative in the front here. So c2 e to the negative x sine of 4 of x. Then we're going to take the derivative of this part right here. And then we get plus 4c2 e to the negative x cosine 4 of x. So now we have the derivative of y of x. And now we're just going to plug this in. So we get negative 1 on the left side of the equal sign, and all of our x's turn into 0. So if this turns into 0, we're going to get negative, for this term right here, we're just going to be left with negative c of 1. For this term right here, if x is 0, it goes away. Same thing with this one, it goes away. And then for this part, if x is 0, we're just going to be left with plus 4c2. Plus 4c2. Bam. So now we just have that. Our c1 is just 1. So we could just get rid of that, put that right there. And then if we add 1 on both sides, we get 0 is equal to 4c of 2. And then c of 2, we find that it's just 0. So there is our other constant. So now we just plug in these constants for a general solution. When we do that, we're going to get y of x is equal to e to the negative x, our c1 is just 1, e to the negative x cosine of 4 of x, and our c2 is 0, so that this part right here completely goes away. So right here would be our solution for this, and for this initial value problem. Sorry if I went a bit fast there, but I was kind of just zoning in. But yeah, right here you would have the solution for this initial value problem. But yeah, hopefully this video helped you guys out, and hopefully that proof was a little, I guess like the proof, I like doing proofs, so I kind of wanted to go over the proof, but hopefully this video helped you out. And yeah, see you guys later.